This video will cover the topic of aromaticity. Aromaticity is the property of some cyclic organic molecules that have multiple conjugated double bonds, and sometimes also lone pairs, that are highly resonance stabilized. The most common example that we see of an aromatic compound is benzene. Remember that benzene is a cyclic molecule that has 3 double bonds. Typically, we draw benzene with 3 double bonds and 3 single bonds. However, spectroscopy shows us that all of the carbon-carbon bonds in this molecule are the same length. This tells us that rather than having 3 single bonds and 3 double bonds, all of the carbon-carbon bonds in this molecule have some single bond character and some double bond character. In other words, it is a resonance hybrid of these 2 contributors. Sometimes benzene is drawn like this, to indicate that it is a resonance hybrid of the 2 contributors, and that all of the pi electrons are equally shared between all of the carbon atoms. The only downside to drawing benzene in this way is that we can't tell exactly how many pi electrons it contains. Benzene contains 6. Due to the high stability of aromatic compounds, these types of compounds do not react in the normal alkene reactions that we have previously discussed. Aromatic compounds like benzene require more harsh conditions to react, and we will talk about these reactions later. Because aromatic compounds react differently than other alkene-containing molecules, it's important to be able to distinguish aromatic compounds from other types of double bond-containing compounds. Aromaticity can be identified in compounds that meet the following criteria. First, the compound must be cyclic. Second, every atom in the ring must have at least one unhybridized p orbital. Additionally, the ring must be planar, which is necessary to allow proper p orbital overlap. And finally, aromatic molecules have rings that contain exactly 4n plus 2 pi electrons, where n is any integer starting with 0. This last criterion is known as Hückel's rule. Now, with these criteria, let's take another look at benzene. Benzene meets all of these criteria. It's a cyclic molecule. All of the carbons in the ring are sp2 hybridized, meaning they have an open p orbital. This molecule is planar, allowing for proper p orbital overlap between the carbons. And finally, it contains exactly 4n plus 2 pi electrons, where n is equal to 1. This identifies benzene as an aromatic compound. Remember that in order to be aromatic, a compound must meet all of these criteria. Some compounds will meet some of these criteria, but not all of them. There is a special case of compounds that meet all of the criteria except for Hückel's rule. These are called anti-aromatic compounds. Anti-aromatic compounds are exceptionally unstable. Let's look at an example. Cyclobutadiene is an anti-aromatic compound. It meets all of the criteria that we previously discussed except for Hückel's rule. It is a cyclic molecule. Every atom in the ring has an open p orbital because they are all sp2 hybridized. We know this because they're all involved in double bonds. And the molecule is planar. We know that it must be planar because it's a cyclobutane molecule with 2 double bonds. Remember that cyclobutane has very little ability to rotate around its bonds because it contains only 4 carbon atoms, and the double bonds add extra rigidity, making this compound planar. Cyclobutadiene does not follow Hückel's rule. The number of pi electrons in this system is 4. This is 4n pi electrons, not 4n plus 2 pi electrons. Therefore, cyclobutadiene is an anti-aromatic compound.